Imagine you have 20 machines and you need to run dozens of application pieces across them. Some machines get crowded. One fails at 3 in the morning. Traffic spikes, and you suddenly need more capacity on the right hosts. Running the application is only half the job. Something has to decide where each piece belongs, notice when a machine dies, restart work elsewhere, and keep the whole fleet agreeing on one shared truth. That coordination problem is the heart of Kubernetes, and it is exactly the problem Amazon EKS was built to take off your plate, at least the hardest part of it. Kubernetes splits the answer into two layers. Call the first the data plane, the muscle. These are the worker nodes, ordinary machines, virtual or physical, where your application containers actually run and use CPU, memory, and network. Call the second the control plane, the brain. It does not run your app. It makes global decisions, where a new workload should land, what the desired state of the cluster is, and how to steer reality back when something drifts. Here is the misconception to kill early. The brain is not a bigger app server. If you open a worker node, you see containers. If you open the control plane, you see decision makers and a carefully guarded store of cluster state. Workers do the physical work. The control plane decides what should happen. Running that brain yourself is expensive in the worst way. Nights spent patching, multi zone failover design, certificate rotation, and the quiet fear that etcd, the cluster's memory, might lose quorum. Amazon Elastic Kubernetes Service, or EKS, is a fully managed AWS service for running Kubernetes. The core bargain is simple. AWS operates the control plane for you. Security patching, version updates, high availability, and distribution across multiple availability zones. You still own the muscle, worker nodes, and the workloads on them. And you still speak plain Kubernetes. But the operational burden of keeping the brain healthy, secure, and always reachable shifts to AWS. With EKS, you still use Kubernetes. AWS carries the control plane. Why does that bargain matter in practice? Three payoffs stack. First, operational overhead drops. Your team stops designing control plane failover and starts writing deployments, services, and policies. Second, availability and security become defaults rather than projects. The control plane is spread across availability zones, patched and updated as a managed service. Third, EKS does not invent a private dialect of Kubernetes. It runs upstream Kubernetes, so the skills and YAML you already have transfer. Kubestill still works, Helm still works, existing applications still deploy. Managed does not mean replaced. Managed means the brain is operated for you while the API you learn stays the real Kubernetes API. That is the quiet superpower. Less toil without locking you into a look-alike platform. Open the brain and the pieces stop looking mysterious. Each one answers a coordination need you already felt. Every request, every tool, every internal component talks through the Kube API server. It is the front door and the single source of truth for what did someone ask the cluster to do. Behind it sits EastTCD, a distributed key value store that holds cluster state and configuration. Lose a consistent state store and the fleet has no shared memory. The Kube scheduler watches for pods that need a home and chooses a worker node based on resources and constraints. The Kube controller manager runs control loops that constantly compare desired state to actual state and nudge the system back. Restart this, scale that, replace what died. And the cloud controller manager is the bridge into AWS itself. Load balancers, nodes, routes, the cloud-shaped edges of the cluster. Notice the pattern. Nothing here runs your business container. Everything here keeps the fleet coherent. Here's the idea that makes every control plane component click. You do not SSH into 20 machines and push containers by hand. You declare a desired state. I want 3 replicas of this pod, labeled like this, reachable like that. The API server accepts the declaration, etcd remembers it, controllers watch the difference between desired and actual. When a node dies and a pod vanishes, the system does not wait for a human ticket. A controller notices the gap and works to close it. The scheduler only places work. The controllers keep reality honest over time. That loop, observe, diff, act, is why Kubernetes feels self healing instead of merely scripted. EKS does not remove that loop. It hosts the loop's brain so the loop keeps running while you sleep. Now zoom into one worker, one unit of muscle. 3 residents matter. The kubelet is the node's local agent. It talks to the API server, learns which pods belong on this machine, and makes sure they are running. The container runtime is the engine that actually pulls images and starts containers, the hands the kubelet uses. Kube proxy handles network plumbing on the node so services can reach pods and traffic rules stay consistent as pods move. So when the control plane decides run this here, the kubelet and runtime turn that decision into real processes, and kube proxy keeps the network story honest. The muscle is not dumb iron. It is a thin, disciplined agent layer sitting on top of compute. Notice the line that appears in every honest architecture diagram, a boundary between the control plane and the workers, crossed mainly through the API server. That is not decoration. The brain never reaches into a machine and starts a process by magic. It writes intent into the API. The kubelet on each worker watches that API, pulls work that belongs to it, and reports status back through the same door. Controllers likewise do not bypass the API server to poke etcd on the side in normal operation. They reconcile through the shared front door so every change is authenticated, validated, and recorded. Once you see that star topology, many components, one hub, the diagram stops being a pile of logos. It becomes a traffic pattern. Intent in, state stored, agents act, status returns. EKS keeps that hub highly available so every agent and every kubesock command has a trustworthy place to talk. What does the scheduler actually place? Not a bare container, a pod. A pod is the smallest deployable unit in Kubernetes. It can hold one container, which is common, or several tightly coupled containers that must share fate, network identity, and storage. That is the misconception to clear. Pod does not mean exactly one container. Each pod gets its own IP address on the cluster network. Pods talk to other pods and to the outside world through that identity, while the platform handles the messy details of where the pod is scheduled. Think of a pod as a small logical host the control plane can place, restart, and replace as one unit. Containers inside are roommates. The pod is the apartment. Follow one pod on its short journey, and the architecture stops being abstract. You apply a manifest. The API server validates it and stores the object. The scheduler binds the pod to a worker that has room. On that worker, the kubelet sees the assignment, asks the container runtime to pull images and start containers, and reports status back. Kube proxy and the cluster network make the pod's IP reachable to the rest of the system. If the container crashes, the kubelet restarts it according to policy. If the whole node disappears, controllers reschedule a replacement elsewhere. You never pointed at a machine and said, "Run here forever." You described what should exist. The brain and the muscle together keep making it true. That is the shift from host-centric ops to declarative ops. Some work should not be scheduled somewhere. It should follow the fleet. A daemon set says, run a copy of this pod on every node, or on every node that matches a selector. That is how you spread logging agents, monitoring collectors, networking helpers, or security tools so each machine gets the same sidecars of operational truth. When a new worker joins, the daemon set notices and places another copy. When a node leaves, that copy goes with it. Pods are how you package an app. Daemon sets are how you stamp node-wide services across the muscle so the platform stays observable and safe as it grows. When do you reach for a daemon set instead of a deployment? Use a deployment when you care about account, 3 API servers, 10 workers handling checkout, and you are happy for the scheduler to pack them wherever they fit. Use a daemon set when you care about coverage. Every node must run the log shipper, the metrics agent, the CNI helper, or the security sensor. Coverage is a different promise than capacity. If a new node joins the data plane during scale-out, capacity workloads may or may not land there, but a daemon set's job is to show up on that node automatically. That is why platform teams love them. The muscle can grow, and the operational sidecars grow with it, without a separate install checklist for each machine. Apps scale by replica count, node services scale by fleet membership. How do you actually get there on AWS? The path is deliberately short. First, provision an EKS cluster. EKS automatically deploys and runs the Kubernetes control plane for you, the managed brain across availability zones. Next, you choose how muscle appears. You can provision worker nodes on Amazon EC2, classic customer managed compute for the data plane. The same workflow diagram also shows AWS Fargate as a path to deploy serverless containers without managing node servers yourself. Then you connect, point kubectl, Helm, or your favorite Kubernetes tooling at the cluster endpoint. Because EKS runs upstream Kubernetes, existing manifests and tools keep working. Finally, you run Kubernetes applications, deploy to the cluster, and let the control plane place pods on the data plane. Along the way, EKS ties into the rest of AWS, VPC networking, IAM for authentication, and application load balancers for traffic. The Kubernetes interface stays familiar. AWS supplies the surrounding infrastructure integration. One more boundary people blur: who runs the app? EKS manages the control plane. Your containers still run on the data plane, on EC2 worker nodes you operate, or on the Fargate path the workflow diagram shows for serverless containers. AWS is not secretly executing your business logic inside the managed masters. Networking lands in your VPC. Identity ties into IAM, so cluster access follows the same permission culture as the rest of your AWS estate. When you need to expose HTTP services, application load balancers integrate instead of forcing a one-off edge. And because the distribution is upstream Kubernetes, the day you debug with kubectl get pods feels like any other cluster. Only the control plane's care and feeding is no longer your pager's problem. Familiar tools, shared responsibility, clear line, brain managed, workloads yours. Step back. Kubernetes coordinates a fleet by splitting brain from muscle, a control plane that stores desired state and drives the system toward it, and worker nodes where pods actually run. Amazon EKS keeps that model and lifts the control plane's availability, patching, and multi-zone operation onto AWS, while you focus on nodes, workloads, and shipping software. Pods and daemon sets turn applications and node agents into declarative units the platform can place and repair. Standard tools like kubectl and Helm still speak the same language. The broader idea is simple and powerful. Managed abstractions let teams describe desired application state instead of babysitting infrastructure. So here is the open question to take with you. If the control plane can continuously repair a cluster toward a desired state, what other parts of application operations could you express the same way?